So what problem are we trying to solve? So what is pose estimation? We're trying to answer questions like this. So where is our robot? Where are we going? How do we get to point B from our current location? You probably have a picture in your head of something like an XY coordinate. And maybe our robot is currently here at some XY location. And we're trying to get to some target location. If we know where we've started, we can use pose estimation and some knowledge of how we've been using our actuators to know sort of where are we at along the path to get from one point to another. So before we go into the details, I'll mention just a couple of things at a high level. We can do this using sort of an external sensor model, or a more internal sensor model. Or better yet, using a combination of both. To start with, we'll go with the internal sensors. So let me first explain external sensors so that the last thing I'm talking about are the internal sensors that'll be relevant for the rest of this chapter. This would be something like using a LiDAR system that we'll pick up in a couple of weeks. That would be a rangefinder. What is the range from our current location to something straight ahead? We could also have a motion capture system. That's something that's sort of a stretch goal for this class, whether we can have our motion capture system set up by the end of the semester or not. These are external cameras. So unlike a LiDAR, which is attached to our robot, the motion capture system would be entirely external and just feeding wirelessly pose estimates to the robot itself, and much more accurately, I would add. And the list here can go on. There are other types of sensors we could use externally, and we'll talk about a few more of those throughout the semester. Internally, we are going to use our wheel encoders. The distinction here between using something like LiDAR, which is on the robot, and wheel encoders, which is also on the robot, is that the wheel encoders are only measuring something on the robot itself. How much has the axle on the motor rotated? And in fact, it only measures how much has it rotated since the last time we checked the count. At some point, that value is going to overflow the integer type, so we're going to clear it periodically as well. And it's not doing something like checking to see if we're actually making progress. The wheel could be not touching the ground. Maybe we got high-centered, the robot got high-centered. Or maybe it's slipping and, a full rotation of the wheel, which is measured by the encoder, doesn't actually end up moving the robot that same distance. Slightly better than just using the wheel encoders, but certainly not fine by itself, would be our inertial measurement units. Which is really just a packaging of accelerometers and gyroscopes. These accelerations and angular accelerations can be integrated over time to get velocities, which can be integrated again to get our positions. That information is extremely noisy, as we'll see in a couple of weeks, so we don't want to rely on either one of these by themselves. But combining the two with a filtering process, which again we'll talk about soon, will actually work quite well for getting us good pose estimates. They work as a nice odometry system. Speaking of which, pretty soon after we introduce the encoders, the IMU, we'll also have our magnetometer. Which measures the Earth's magnetic field, and we can use that to figure out if we're heading north or some other cardinal direction. So now that we have a little bit of an idea of what we're trying to do with pose estimation, and we know what kind of data will be available, let's start formalizing this framework, starting with our reference frames or coordinate systems. Largely speaking, our pictures for the rest of the semester will look a lot like this. Our robot is not going to be flying around, so we're not going to worry about a vertical z-axis. We'll define a unique point in space called the origin, and we'll define an x direction, and at 90 degrees from the x-axis, we'll define a y direction, and we'll define a direction of positive rotation. And mostly arbitrarily, but just sort of for the sake of convention, we're going to be using a right-handed coordinate system for our reference frames. Really, all that means is we're defining the direction of positive rotation. So if you point your index finger on your right hand in the direction of x, and your middle finger in the direction of y, your thumb will be pointed straight up in the direction of z. And we'll define, if you now point your thumb in the direction of z and curl your right hand fingers, we'll define that as the direction of positive rotation. These are all just by convention. There's no reason we have to define them in this manner. We'll also define, using capital letters, a specific global reference frame. So we'll call this x sub g and capital Y sub g. And those are going to be the x and y coordinates for our global frame. Now let's look at a more specific frame. Let's have the mobile robots frame. And this is going to be our wheeled mobile robot. And I'll refer to that as our WMR for the rest of the slides. To start with, I'll just draw it in this direction. So here's our WMR. It has two wheels. This is a differential drive WMR. Has two wheels and a caster ball. And this system is going to have its own local reference frame. So it'll have its own origin. And it's convenient, and you'll see why as we move forward in these slides, to define the origin at the center point between the two wheel axes. And the reason for that is because if we drive one wheel forward and one wheel backward, it'll actually rotate around this center point, assuming we're driving them at the exact same speed. And also for convenience sake, we'll define its x-axis as forward. So we'll call that XR for our x of our robot. And just like for our global frame, with respect to the x-axis, our y-axis is going to point off to the left. So we'll call that the y of our robot's frame. And if we take this picture, and rotate it. The key is, for the purposes of the robot, the X and Y frame does not change. The XR-YR frame does not change. X is always going to be forward from the center of the robot. Y is always going to be off to the left. We can always refer to our left wheel and our right wheel. It doesn't matter which way we're facing in terms of the cardinal directions, whether we're facing north, east, south, or west. And more importantly, it means if we take our robot and put it in our global frame, we'll always have two coordinate frames that we could be referencing: the local frame of the robot and the global frame in which the robot can be found. What we'll try to find out next is there any way to figure out a mapping between the local R frame and the global? And same for the Y, some mapping between YR and YG. That way we can talk in using two different frames. We could say go forward. And we would clearly want to do that in the local frame. It's much easier to say go forward, which is equivalent to just saying travel in the XR direction. On the other hand, we might want to say something like go to a point that is rightmost in our G frame. So maybe that point exists here. There's nothing to the right of this point, for example. And it would be annoying to specify that in terms of this local frame, because it would change over time. If the robot was facing this way, well, from a robot facing this direction, that rightmost point in the global frame would be backwards. However, if the robot were facing directly at it, it would be forward with no Y component. Throughout the semester, we'll develop an algebra for reference frames. With common operations like what happens if you add or subtract reference frames, but more importantly, what happens, or how do you transform from one to another? So if I'm saying let's say the robot and its local frame is going forward, how does that translate to changes in XG and YG depending on the direction of the robot, which could be facing in any direction? Speaking of any direction, let's talk about configuration space. So this would be a description of the robot with respect to a defined reference frame. And we almost always mean the global reference frame. The one slight change to that is if we're talking about a translation. So where are we in relation to our previous local reference frame might make sense under some circumstances. But normally we care about where is the robot in a global configuration space. The configuration space really just describes where the robot is in that global reference frame. So you can think of variables that might be important for that. So for example, we might care about the X location, the Y location, the heading, and I'll use theta for heading. And that's all in reference to the global reference frame. So instead of subscripting each value there with G, I'll just subscript the entire set of them. We might also care about other parts of the configuration. So what else can we change with respect to the robot? What else haven't I specified? Well, in some textbooks, you'll see x, y, and theta. And then you'll also see a reference to the left and right wheel rotations. So, for example, if I draw the wheel, and then I'll arbitrarily just mark the wheel with a line so that we can tell when it's rotated. It might be, for some reasons, it might be important to figure out when the wheel has been rotated. So these would be two separate configurations. And we would want to define a 0 angle, and maybe this is closer to 35 degrees. For the most part, we're not going to care about the exact rotations of the wheels. You've probably never looked at your robot and really cared, are the wheels at 30 degrees from where they started, or pi radians from where they started? That's not typically a question we're going to care too much about, but you can specify things like that. And if this were a robot in 3D space, you can imagine we might have, as a little aside here, something like a 3D multi-rotor model. That might be a quadcopter, a helicopter, something with multiple rotors. Maybe you would care about x, y, and z, so its coordinates in 3D space, and then also its rotation on 3 different axes. And I'll leave this as an exercise for you all. If you think that those 6 numbers is enough to define a multi-rotor in 3-dimensional space, feel free to ask on using Hypothesis on the course website, or asking on Slack if you want to give an answer and have a response. And before we move on, I'll mention a couple other things that you might consider as part of your configuration space. And these would be constant values. So unless your robot is extremely boring, x, y, and theta are going to be dynamic, meaning they change. They're part of these constant values could also be considered part of the configuration space, but we normally leave them out of that set just because they are constants, and, well, they're constants, they do not change. So this would be your wheel radius. And maybe your track width. So clearly, looking at this diagram on the side, the bar that I've marked here also doubles as being the radius. And I'll normally write that with a lowercase r. Track width is often, we often use a symbol of D or capital L for that. And going back to our diagram here, I'll steal out our WMR. Track width is the distance between our wheels. Let's wrap up this video by talking quickly again about what our goal is. So to put it simply, our goal is to estimate the pose. We're going to estimate the pose of our robot from wheel velocities. Pose itself is worth defining as the location, so the position, and orientation of the WMR. Which for us is just a single rotation value. So you can think of position as our XY configuration, and orientation as our rotation, our theta rotation. We're going to make some assumptions. We're going to assume a constant velocity. We'll assume a constant velocity model, which means we're not going to be worried about accelerations. Our robot doesn't instantaneously go 16 centimeters per second, but we're going to make that assumption here for simplification. We're also going to ignore wheel slip and compaction. Our wheels aren't always perfectly 7 or 8 centimeters in diameter. Particularly if you have rubber wheels or rubber bands on your wheels, there's going to be some slight variations there as your robot hits bumps and debris on the ground. But that is a nice place to stop before we start getting into the actual equations of motion for our robot.